All right, so this is the first of the last 3 lessons in which look at a few applications of integrals. Not going really into depth with any of these things. That would be done in a course on integration, but introducing some of these, a few different common applications of integrals at these early stages. And so today we want to look at using integrals to find the area between curves, which is fairly straightforward in idea, since a common way of understanding an integral is the area beneath a curve. And in general, if you want to find the area between 2 curves, you want to find the difference between the 2 functions from some interval of a to b, whatever those are. And you may have noticed there's absolute value brackets here, and that's just essentially when we're talking about the area between 2 curves, it doesn't really matter if it's above or below the x-axis. We're just counting everything as being a positive, like just the total area, and that's what those absolute value brackets there essentially essentially denote. With that said, though, let's look at this. I have 2 waves. I have the sine wave and the cosine wave, and you can see the cosine wave right here and the sine wave right here. And I want to find the area between them in the interval from 0 to pi over 2. So that's what we're trying to find, that shaded region there. Well, that shaded region there, I can denote with an integral like this. It's the integral from 0 to 2 pi, not 2 pi, pi over 2, of the absolute value of just one function minus another. Now, if we're dealing with the absolute value, it doesn't really matter which one we put first. I'll go cosine x minus sine x dx. Because like I said, if I change the order of make it sine x minus cos x, the absolute value will be the same. So that's it. How do I find the area of this? Well, really what I want to do is break it up into 2 chunks and realize at this point here, which is pi over 4, in this first region, this is where cosine is greater than sine. In the second region, this is where sine is greater than cosine. And so in this case, one option I have, although I will at the end mention a slightly faster way, but is to break this up into 2 separate integrals. The integral from 0 to pi over 4 of cos minus sine, because cosine is greater than sine, and the integral from pi over 4 to pi over 2 of sine minus cos, because in that region, sine is greater than cos. So I'm going to break this up like that. Although again, if you think you can realize a slightly faster way of approaching it, you may very well be correct, and I will mention that at the end. All right, so now looking at each of these, while I got a couple of integrals here, the good thing is to integrate them or to find the antiderivatives is quite straightforward because it's just matters of sine and cosine. So if I look at this integral right here, I can see the antiderivative of cos x minus sine x is sine x plus cos x. That's the antiderivative of that. And so I want to evaluate that integral from pi over 4 to 0. Minus, sorry. I could go back and re-record this, but I'm too lazy to. Yeah, there's a minus right here, but when I broke this up into 2 different integrals, I should be adding the 2 because again, I'm trying to find the total area. So please excuse that mistake, put that little plus sign there. Again, I'm finding the area of the area, the part I've shaded here in red and the part I've shaded in blue. So, but I'm adding the 2 up. So, hope you forgive me, even if you don't. I can't hear you. So now I'll find again the antiderivative of sine x minus cos x, which in this case is minus cos x minus sine x. And again, I want to evaluate this integral from pi over 2 to pi over 4. All right, so at this point, sine x, the sine of pi over 4 is 1 over root 2, plus the cos of pi over 4 is 1 over root 2, minus the sine of 0 is 0, and the cos of 0 is 1. Again, I could, I guess, put brackets around here, make that a plus sign, but again, why not just leave it like this? Over here, I'll be a little bit more careful here because there's a few more things going on, but I got minus the cosine of pi over 2 is minus, or is just 0, or minus 0. Minus the sine of pi over 2 is 1, so all of that. From that, I'm subtracting pi over 4. So minus the cosine of pi over 4 is minus 1 over root 2. Take away the sine of pi over 4, which is again 1 over root 2. Okay, so at this point, it's a bit messy looking, but in the end, it simplifies down. If I collect like terms and do all this stuff with the brackets, it comes to 4 over root 2 minus 2. That said, well, that answer is fine. You may recall that technically a radical in the denominator is not in lowest terms. So if I just multiply the numerator and the denominator of this by root 2, notice I get 4 root 2 over 2 whole minus 2. Clearly I can then cancel this, reduce this down, and I do get what I think is a simpler expression, 2 root 2 minus 2. All right, and so now just a quick little note, because I did say there was a faster way of approaching this. If you notice from the start that these two regions are identical, then really, once you realize that, which, especially when I give you the graph, you can perhaps notice quite quickly, then I just got to pick any one of these, maybe this one here, evaluate that, and then times 2. I'll get the same thing. And if you didn't realize that, not a big deal. Like this didn't take that long either. But symmetry is a very nice thing when you're dealing with finding areas. All right, so let's look at this. So again, I have the graphs of two curves, and I want to find the area that's been shaded there. And again, the graph in blue is this 4th degree polynomial, and the graph in red is this rational radically-ish function. All right, so if I want to find the area of that shaded region, I can see that's from 0 to about 1.181. So that's the bounds of the integral. And I can see in that entire region, the function in red, x over root x squared plus 1, is always greater than the function in blue. So instead of dealing with the absolute value, I know that whole region, I can, I always get a positive value if I go red minus blue. With that said, let me start writing some stuff down. So the integral of 0 to about 1.181. And again, it's not wrong at all to put the absolute value brackets in here. But like I said, in this interval, x over root x squared plus 1 is always greater than x to the power 4 minus x. So those absolute value brackets are inconsequential, which is nice. And so I'm going to, at this point, I'm going to break this up into two separate integrals because the integral in red, this one here, is going to be a little bit more work to differentiate, to integrate than this one here, which I can just integrate really quickly. So I'm going to break this up into integral from 0 to 1.181 of just this minus this integral. And so the integral on the right, that one again I can integrate that really, really quickly. The one on the left will require using substitution. And so I'm focusing on what's highlighted in yellow here. I want to say let u equal, I'm going to assume x squared plus 1 is the inside function, therefore du will equal 2x dx. And the good thing is I can see the x, the dx, I just got to put a 2 there, put a 1/2 here, and it's all balanced out. So yeah, I can integrate this fairly nicely now. I'm going to focus on just the indefinite integral for a bit before I come back to this definite integral right here. So I can now say 1/2 the integral of 1 over root EU du. I can look at that, or even better, 1/2 integral of u to the negative 1/2 du, which, find the antiderivative, is 1/2 times 2u to the positive 1/2 plus some constant. How convenient, the half and the 2 cancel out. So we get u to the 1/2 plus some constant. That's my antiderivative. However, what I really need is this part here, the square root of u, which is x squared plus 1 plus some constant. That's it. I can now, what I really need is this here, and I can now evaluate that from my bounds, as well as the other part up there that I've highlighted in blue, which I don't need to use integration by substitution to evaluate. So putting this all together now, I can really now evaluate this. So I'm going to evaluate root x squared plus 1 from about 1.81 to 0 minus the antiderivative of x to the power 4 minus x, which I'll just do quickly right here. All right, and at this point, I'm now just typing a bunch of stuff into my calculator. So I will say, well, you can do this all on a calculator in one step. I would do it in a few steps. The integral on the left from root x squared plus 1, when you evaluate that, you should get about 0.5475, and the one on the right should get about negative 0.2379. You're subtracting that, so it's the same as adding them, so you should get about 0.785. And so keep in mind again, if I go back to this step, these steps right here, I had one single integral. I broke it up into two integrals just to make it easier for me to integrate. Essentially, because this part here that I'm underlining in green did not require any integration by substitution, so I know it's going to be relatively easy, and I can focus on them two separately. All right, so the last example is right here. And again, I have a couple graphs. The graph in blue is not a function, y squared equals 2x minus 6. And the graph in red is a linear function, y equals x minus 1. And I want to find the area between these two regions, this area here. All right. So for a question like this, we're actually better off to visualize it if you kind of imagine turning your page 90 degrees. Now I can't really do that on, I can't really do that on my iPad right here. But imagining looking at your screen so that the top is this way, and therefore this is the bottom. And imagining your x and y's all being swapped around. Or really, in this case, this is much more straightforward if I choose to eventually integrate with respect to y instead of respect to x. Because if I want to integrate with respect to x, if I want to look at the question kind of this way, the problem is these little regions here are tough to find the area of because that region there is not a function. But if you look at this the other way, like I'm kind of encouraging, and again, if you take your screen, your page, whatever, and rotate it so that the top is pointing up this way, you have a line and a parabola opening up. And the line is greater than the parabola. And that's, you can think about it that way as long as we just differentiate. What we're really doing is we're thinking about differentiating with respect to y instead of x, which means the bounds we're differentiating between, I want to pay attention to the y coordinates from -2 to 4. And so this region that I want to find, I can express as an integral, as the integral from -2 to 4 of the function that's greater in terms of x, right? Usually we think about the function that's greater in terms of y, but I'm thinking about everything kind of flipped around. So of these two functions, the one in this region that always has a greater x value is the one in red. So of x minus 1, and all of that minus the function in blue, which in this case, what do I write down here? I need to have my equations in terms of just x. Right now I have my equation with y squared. But again, I want it in terms of, ooh, what am I doing? Oh, I made a mistake. I'm far too long in this video to re-record this. Everything I said is pretty much right except what I wrote down here. Because again, I said I wanted to integrate with respect to y, and I started writing down stuff in terms of x. And again, these bounds here, -2 and 4, that wasn't with respect to y. Everything has to be with respect to y. So looking at, again, this function here, I need to solve it for x instead. I need to, right now it's solved for y. I need to have everything the other way around. And so if I take that y equals x plus 1, I can rewrite that as y. If I look at that y equals x minus 1, I can look at that as y plus 1 equals x. And so that is going to be the first part of what I'm going to have here. All that minus, if I look at the function in blue, which was y squared, or relationship in blue, equals 2x plus 6. If I solve for x, I get y squared minus 6 equals 2x, or x equals 1/2 y squared minus 3. And again, I need everything to be in terms of y, like I have there, like I have right here. And so my integral here is going to be minus 1/2 y squared minus 3 dy. And let me just give myself a bit of space here. There we go. And so again, I completely appreciate, especially with the few mistakes I said, that it's harder to think about an integral like this where everything's in terms of y. But really we're imagining, again, instead of finding the area kind of going this way, which is in terms of with respect to x, we're finding the area in little slices going this way. All right, with that said though, just like when you're differentiating, you don't have to differentiate with respect to x. We don't have to integrate with respect to x. And in this case, it's easier to integrate with respect to y. However, I think the hardest part of the question is now set up. So now, again, I can, I could, like the last question, break this up into a couple of integrals, but everything here is just a power. So I'm just going to combine like terms here. And you should get, I'll write my highest power first, negative 1/2 y squared plus y plus 4 dy. And now I'm going to find the antiderivative of this, which again, I don't need to use substitution or anything. Just use my power rules. And when I find the antiderivative of that, I should get negative 1/6 y cubed plus 1/2 y squared plus 4y. And I want to evaluate this from 4 to -2. And now at this point, the hardest part is definitely done. This is just a matter of substitution now. Substituting in these values. I'll write this step out, but you can do, it's probably kind of boring just to watch me write this all out, but 1/6 times 4 to the power of 3 4 to the power of 3, which is 64, and so on. All right, so again, 64 is 4 to the power of 3, 4 to the power of 2, 4 to the power of 1, -2 to the power of 3, -2 to the power of 2, -2 to the power of 1. Do all that good stuff, and you should get exactly 18. Oh, what a lovely number. And again, this idea this question was made, becomes much more straightforward when we just accept we don't have to integrate with respect to x. And that ends the lesson.